Okay, that's kind of loud, huh? So what we did was, before we started recording, was just review what we had done last time, which was a fairly extensive analysis of this sum of sinusoids with different frequencies, which we never did a hand plot of this, but we did a GeoGebra plot. And I actually suppose we could repeat that. Do you remember what it looked like? I have the GeoGebra here, so I just need to minimize these guys. Oh, I was plotting something else here. Okay, where is that? Applications here. I'm going to say that, and we have sine of x plus sine of 2x. Huh? And we see that, yeah, it doesn't repeat the sinusoid. It does repeat something, right? Let's kind of zoom in on the axis and maybe see, if we zoom in like this, we can see very clearly, yes, it's repeating over and over again this same shape. And what is that shape and what is its periodicity? Well, the periodicity is 2 pi. That's the period of the sine x, right? Sine 2x has a period of half of that, but if one of the things you're adding together has a period of 2 pi and the other one has a period of pi, then the period of the sum will be 2 pi, the larger of those, right? So I can say plot, I think it's 2 pi minus 0, right? The stopping point of that form, or the end point of that. It doesn't necessarily stop there. It goes on forever and ever and ever into eternity. So yeah, so we were looking to see where these maxims, and boy, that was a lot of work. It took a lot of time, is what it did. All right, so Kyra, I did get your name, but I think you're right. I didn't. No, I didn't. You're right. Wait. Oh, I did. Yeah, I see it now.
Okay, thank you.
Sure, you bet. And Xavier, okay. I think I missed you. All right, very good. So back to our DocuCam. That's the calculator. Okay. So that's tangent. Okay. So I think what we need to do next is secant. All right, let's do a secant. And I want to be careful not to show just the white sheet here. So let's set it up for secant, right? So for secant, here's the function. There's something about the algorithm of this camera's focus that if it just sees white, it can't focus, which kind of makes sense when you think about it. What are you going to focus on? There's nothing there. So we'll make a table of values, and how about we just, I was about to call it theta, which is a common input for secant. But I want you to be accustomed to using x as the input for a trig function, even though that's confusing because when you're thinking unit circle, that's a different x, right? That little bit of cognitive dissonance should not throw you. All right. Oh no, there we go into non-focus. I have to put my hand down when that happens. And no, can't do it. Let me put down writing. Yeah, if it doesn't get enough writing, it can't handle it. Or something. I don't know what it is. More light. More light doesn't help. I wish I brought that. I put it in a bag with some other stuff that I wish I had and left the bag. Hello, focus. How about if I bring it closer? And now it's in focus. Move it slowly back down to the sheet. Can you maintain your focus, dear camera? Okay, so there is our table of values coming into, and what are the usual suspects? Well, you know, why do we pick pi over 6 and pi over 4 and pi over 3? Because those are places where we know exact representations. Oftentimes they involve square root of 2 and square root of 3. So, you know, the decimal approximation comes to bear, but at least we have something, you know, that we can approximate. It's a lot easier to approximate the square root of 2 than it is to approximate the sine of 2. Right? What's the sine of 2 is one of those places where you have irrational outputs that are hard to compute. But so, and why is it easy to compute? You know, pi over 6, sine and cosine for pi over 6 and pi over 4 and pi over 3. Well, for pi over 6, you've got your equilateral. Well, pi over 3 is that triangle. When you bite one of the angles, you have 2 right triangles with an angle of pi over 6 and one. The 2 angles are pi over. Shall I draw a picture of this? Just to, yeah. So how do you construct a equilateral triangle? Little sidebar here, folks. Well, you draw a circle. No, did it right in the middle of my. And then you put your compass on the circumference of the circle, and you draw another circle of the same radius, right? We go through the center of the original circle, right? So now what have we got? Well, we join the 2 circle centers, which are here and there. I think I'm looking at that the right way. Whoops, kind of wavered there a little bit. And then you join this point at the top. Now, both of these circles have the same radius, right? So they share that one radius I've drawn already. And then these 2 radii are congruent to those, right? And whoops. Kind of made a mess of it. The equilateral, right? And so this angle here is pi over 3. Well, I refer to the angle as pi over 3, but you know, if they're all length 1, then these are circles, right? And that means the arc here is pi over 3. And we're going associating, you know, the central angle subtended by that arc with the arc on the unit circle. So we, you know, associated the central angle with the arc with the degree measure of the central angle. This is actually the radian measure, which we will define radians soon. We haven't done that yet, right? But then if I drop a perpendicular down here to the base, I'm just going to pretend this is perpendicular. Looks close enough. Then it bisects the opposite side, right? And so each one of these must be a half to make a whole, right? 1/2 plus 1/2 equals 1. And so then I have an equilateral triangle where I don't know h, the height of the triangle. And that's the y coordinate, you know, if we're talking about, you know, a coordinate system here, where would we put our coordinate system? Something like this, maybe. So the first circle on the left is the unit circle. Sorry, I'm digressing a little bit from our secant function. We'll get back to that in a minute, but I want to sort of emphasize, why do we always pick these pi over 6, pi over 4, pi over 3? Well, because in particular, pi over 6 is half of pi over 3. That's this angle here. I'm referring to it as a measure of the angle because if we were to bisect this angle pi over 3 here, we get 2 pi over 6s comprising this pi over 3 arc, right? So we get 2 arcs of pi over 6, which 3 arcs of pi over 6 make pi over 2, which is how we know North Pole, right? So in any case, what is h? Well, we use the Pythagorean theorem, right? We say h squared plus h over 2 squared. Those are the 2 legs of this, what I'm looking at trying A, O, should we call this C, call this B? AOB is equilateral, and triangle AOC is a right triangle with acute, I can't help but call them angles, right? This is how we measure the angle as to what it would make on the unit circle. So this arc clearly makes pi over 3 on the unit circle, and this one makes pi over 6. So then, yeah, so we're getting, we're using the Pythagorean theorem here to say, you know, what is h? What are the coordinates of a? Well, clearly the x-coordinate of a is 1/2, which says the cosine of pi over 3 is 1/2, or we can fill in the table, right? We're kind of interested in then what is the cosine of pi over 6, and that is going to be what h is, it turns out. So this is 1 by the Pythagorean theorem, the 1 squared, if you like. I mean, that's the right triangle. AOC has legs h and 1/2. Oh, I'm sorry. I put an h over 2. That should be a 1/2, right? Is that better? Yes, it is. Okay, so the x-coordinate at A is 1/2. What's the y-coordinate? Well, that's going to be this h value, right? So we say that h squared is then equal to 3/4 because 3/4 plus 1/4 is 4/4, which is 1. And that means that h, if h is positive, which it is here, then it's going to be the square root of 3/4. And the square root of a ratio is the ratio of square roots. The square root on the top is the square root of 3. And the square root on the bottom is 2, right? The square root of 4. And so that's how we get h. Now, if you were to take this triangle AOC and rotate it around so that the side OA bisected that pi over 3, then you would get that the x-coordinate at that position was h, right? And that's square root of 3 over 2. So the cosine of pi over 6 is square root of 3 over 2. I've kind of used up my space over here, which I don't want to do. Boy, ever since I got away from these Sharpies, I've been doing a lot of erasing. I have to buy a new eraser. Okay, so so this is 1, right? The cosine of 0 is 1. So the reciprocal of 1, well, that's easy, right? The reciprocal of square root of 3 over 2 is 2 over the square root of 3, right? And for that, what do we want to say? We want to say, get over here, 2 over the square root of 3. Well, you multiply the top and the bottom. You learn this trick in your algebra class, right? That if you multiply by 1, which, you know, anything divided by itself is 1, then you multiply the numerators, you multiply the denominators, and you get now an irrational number in the numerator, twice the square root of 3, but you get a nice rational number in the denominator, yeah? So 2 root 3 over 3. Can we approximate that? Yeah, much more easily than 2 over root 3, right? If you were to do 2 over root 3, what would you be doing? Well, you'd say that's approximately 2 divided by 1.732, which is 2,000 divided by 1,732. You could say, well, that's 1,000 divided by 866. What you could say is 500 divided by, just reducing the lowest terms right here, one factor of 2 at a time. So how are you going to approximate that? Well, long division, right? How many times does 430? We're doing a lot of computation again. How many times does, what goes in once, huh? And the remainder is 67. Goes in once again. The remainder is 137. Goes in 3 times. So now we have a 3-digit approximation. We had originally a 4-digit approximation, so maybe we can get one more digit out of this. So 3 times that is this. Subtracting, we get 71 and 433. It's closer to 2 than to 1, right? So I'm going to put a 2 there. But let me show you the reason for rationalizing the denominator now, right? Which is, if I say 2 root 3 over 3, I can say, well, that's approximately twice 1.732 divided by 3, which is, equal to, this is easy to multiply by 2, is it not? 3.464. And now I'm just dividing by a single digit. That's a lot easier than dividing by, trying to make this straight down, my writing is angle. So yeah, do you see it goes in once again, and 5 times? Uh-oh. I think I screwed this up, didn't I? Oh yeah, this should be a 2 here, huh? Yeah. So this is a 5. So I screwed that up, which I think, just kind of points to, so these are wrong then, right? Which points to the fact that, yeah, that's why you should rationalize the denominator, because it's a lot easier to divide by a single-digit number than by a 3-digit number. And so this is a 5. Did you see that mistake when I was making it and you didn't say anything? If you see something, say something. So I think another 5 here, huh? Okay, so this value here, secant of pi over 6 is approximately, well, it's 2 divided by square root of 3, which we've shown is approximately 1.155. Okay, so what's going on at pi over 4? How do we know the exact value of the cosine of pi over 4? Well, for that we have an equilateral, an isosceles right triangle. And I won't bother you with the derivation of that. It's very similar to this, but we get the square root of 2 over 2, which is a familiar number, right? So we can compute that exactly in terms of radicals. Now we would like to approximate its reciprocal. So the reciprocal is 2 divided by the square root of 2, but I'm just going to write, for simplicity's sake, that that's equal to the square root of 2, right? In fact, one way of looking at the cosine of pi over 4 is it's the square root of a half, which is whose reciprocal is the square root of 2. And that's approximately 1.14. 1.414. Yeah. And then the reciprocal of 1 is 2. Sorry, yeah, the reciprocal of 1/2 is 2. So how are we doing? Yeah. Do we have enough to do a plot? Well, remind you that the cosine is an even function, right? Which cosine of negative x is the same as the cosine of x. And so secant is also an even function. And so we get twofers for each of these, right? Plus or minus pi over 6 will give you secant is 1.15. And plus or minus pi over 4 will give you that. And so what happens is we go to pi over 2. Well, pi over 2, the cosine is 0, right? We're at the North Pole here, where the x-coordinate is 0. Yeah, the x-coordinate, there's that cognitive dissonance. That's a different x, right? And then what's the reciprocal of infinity? Sorry, what's the reciprocal of 0? Well, it depends on whether you mean positive 0 or negative 0. Oh, there's the same number, aren't they? Well, I mean, whether you're approaching 0 through positive numbers or approaching 0 through negative numbers. So you get something that's, let's say, plus or minus infinity, depending on which side of 0 you're on, or you're approaching 0 on. And that's true for plus or minus pi over 2. So let's make a plot with what we have so far. Okay, so here's my x-axis, right? This x, the x here, right? And here's the y-axis, which is the output of our secant function. Okay, and we want to plot these numbers, right? And between, let's say, negative pi over 2. So here, I'm going to say here's pi over 2 and here's negative pi over 2, all right? Those perfectly evenly spaced? No, but it's close enough. Okay, so here we got a vertical asymptote, right? Because the output of secant is approaching infinity or negative infinity, but the reciprocal of 1 is 1, right? That's this value here. And then here's 2, where that's at pi over 3, which is 2/3 of pi over 2, right? You get pi over 6, 2 pi over 6, 3 pi over 6, right? And pi over 4 is the midpoint, halfway between. So are these perfectly evenly spaced? Well, what's missing? What's missing is pi over 12 here and 5 pi over 12 here, right? So you go 12, 2 pi over 12, that's pi over 6. 3 pi over 12 is pi over 4. 4 pi over 12 is pi over 3. 5 pi over 12, and then 6 pi over 12 is pi over 2, right? That same old rigmarole. Okay, so at pi over 3, we have 2, right? At pi over 4, we have less than 1.5. We got about 1.4, and then this is about 1.1, right? And we got the same values on the other side, right? So right about there, right about there, and there. And, you know, so it looks like a U-shaped thing. It is kind of, right? It's not a parabola, mind you, right? A parabola is a quadratic function of polynomial squared plus something x plus a constant would be a parabola. This is not a parabola. This is the secant function, which is the reciprocal. So where's cosine here? Well, cosine function here, right? It's just, yeah, it's doing that, right? So the reciprocal, well, the reciprocal of a number less than 1 is greater than 1. The reciprocal of 1 is 1, and it's approaching, as cosine goes to 0, the reciprocal goes to infinity, both at negative pi over 2 and pi over 2. But so what happens over here? Here's pi over 2, here's pi, let's say this is 3 pi over 2, and this is pi. And so you can have another vertical asymptote here because the, you know, at the South Pole, x is 0, right? Well, x on the unit circle is 0. So if this x is pi, then that has a cosine of 0. Sorry, that has a cosine of negative 1. Oh, that pi is over here. 3 pi over 2, as I was saying, is the South Pole, and that's where x is 0, right? And the reciprocal is going to go to negative infinity. So these values are just the flip of these values here. And I'm not going to bother to plot individual points. We're just going to say it's the same exact shape except upside down. And oops, a little bit, yeah, a little bit misshapen there. Maybe more like that. I didn't plot exact points. Should we do it on GeoGebra to see a clean plot of secant? Sure. So let's plot both secant and cosine. Let's plot cosine. All right. Here's cosine x. Point of reference, right? Shall we make it dotted? Because that's not our direct object of plotting here. Is should make it less. Okay. All right, so there's a sort of ghost of a cosine function, right? And let's bring down the scale on y a little bit, right? Okay, shall we draw in the asymptote? So x equals pi over 2 is a vertical line, an asymptote. X equals negative pi over 2. That's a vertical line. That's an asymptote, right? How about x equals 3 pi over 2? It's also a vertical line. So can I choose these 3 vertical lines and say properties? Yeah, how about the color? We'll make it the same sort of mauve. And style will make them also dotted and maybe a little bit more ghostly. Yes. So you kind of see those in there. They're going to give our secant function shape, right? And how after secant and see how it fits into these other things, right? So when cosine is 1 or negative 1, well, the reciprocal of 1 is also 1, and the reciprocal of negative 1 is also negative 1. So that's where the cosine and the secant functions intersect. But whereas cosine is confined to the interval from -1 to 1, secant is either larger than 1 or less than -1. It's never in between. Yeah? Okay. And it's periodic, right? So just repeats that same waveform again and again and again. All right. And what about cosecant? Well, it's the same shape shifted pi over 2 to the right. So in fact, if I were to plot f of x minus pi over 2, that's the sine function, right? Can you see that's what I typed in? Let me go to my speaker view so I can see what we're looking at here. Yeah. So I typed in cosine of x minus pi over 2. You can see from the graph that's exactly the same as sine x, right? It goes through 0, 0 and rises up to 1 at pi over 2 and drops down to -1 at 3 pi over 2 and it's back to 0 at 2 pi. Well, I think I can scale my axes so that they're not 1, 2, 3. Instead, they're multiples of pi over 2, the labels, but no, that's all right. So what about the reciprocal of that? Okay, I gotta go to my, I can't look at the, now. So I'm gonna say, give me P of x minus pi over 2. Right, that's the cosecant function, right? So you see, just as sine and cosine are horizontal shifts from each other, secant and cosecant are also horizontal shifts from one another. You know, take the secant and shift it pi over 2 to the right, you have the cosecant. So That's what I have to say about that. Let's see what exercises we have in the book for that. And for the book, we can go to Sumatra. And in Sumatra, I think we can sort of maximize things a little bit by zooming in here. So this is more trigonometric graphs. We've talked about the graphs of tangent. We didn't do cotangent, did we? Well, I'll tell you what, let's go over here and save this thing so we can bring it up again if we want it. Save as, I guess I'll save it here as secant cosecant. And then let's choose everything, delete it, and make a plot for tangent, which is similar to the other one, right? So I'm going to say, okay, so here are my vertical asymptotes, the same ones for secant, right? Because secant and tangent both have cosine in the denominator, right? Secant is 1 over cosine, and tangent is sine over cosine. So that's they have the same vertical asymptotes. So I can say, you know, negative pi over 2. That's, oops, what happened there? Oh, I wanted to make a slider of it. I have to say x equals that. Okay. And then x equals 3 times that. Oh, well, let's just say 3 pi over 2. That's a vertical asymptote. Also 5 pi over 2 for that matter, right? X equals any odd multiple of pi over 2. Oh, I don't want to create a slider. I thought I had typed in a division sign. Apparently I hadn't, right? So if we plot tan x here, oh, TNA, doesn't know TNA. Okay, so, oh, I didn't want that. Oh, we're doing that. Okay, so there's the tangent function. So what about the cotangent function? Well, if I just shift this thing pi over 2 to the right, I get cotangent of x. Oh, no, I'm sorry, I was wrong about that. Yeah. So this is not only a shift of pi over 2 to the right, it's also a reflection in the y-axis. Or in the x-axis? Yeah, let's say in the x-axis. So why is that? Well, if x, y are points on the unit circle, then tangent is the ratio of y to x, sine to cosine, and cotangent is the ratio of the reciprocal of that, right? The ratio of x to y. So you're basically swapping x and y. So you're actually getting a reflection in the line y equals x. Because you're swapping x and y. Is that true? I have to think about that. In any case, if we were to tabulate values for cotangent, we'd get the blue curve here, right? And notice that the asymptotes for the blue curve are the asymptotes for the tangent curve shifted pi over 2 to the right. So the asymptotes are shifted pi over 2 to the right, but then the function itself has some other symmetry going on here, which means instead of increasing, it's decreasing. And let's see, if the ratio of y to x is always increasing, which is true, that means that the ratio of x to y, the reciprocal, is always decreasing, right? If a number is increasing, then its reciprocal is decreasing. So you can see that we're always increasing on the red curve, which is tangent, and always decreasing on the blue curve, which is cotangent. All right, so now we can look at the exercises for that section. And what are we reading here? In this section, we graph the tangent, cotangent, secant, and cosecant functions and transformations of these functions. Right. Yeah, we can, in as much as there's a lot of symmetry between these functions, you can also do shifts and stretches of the functions themselves in the dual way, right? So they're making the point about the vertical asymptotes. They plot the points much as we did. For secant, they did pretty much the same thing. So there's tangent and secant, and then transformations of tangent, cotangent. So if you apply the output, you'd stretch it vertically. So that's the case here where the y is twice tan x. That's a stretch by a factor of 2 vertically. And the reflection in the x-axis, you get something that looks a lot like that cotangent curve, except it's not shifted pi over 2 to the right. So here are general transformations where you stretch or compress both the input and the output. So both horizontally and vertically. Graphing tangent curves. So here's one that's shifted pi over 4 to the right. First it's, what is that, a stretch or a compression? X has got to be smaller. So this is the factor of 2 compresses horizontally by a factor of 2 towards the y-axis, right? And then after you do that, you do a shift of pi over 4 to the right. And whatever that leads to, right? So the graphs of transformations of secant and cosecant, again, they're stretching, shrinking horizontally or stretching, shrinking vertically, and shifting. So the same sort of things we've been doing for sine and cosine, you can do for the other 4 trig functions, right? Oops, just maximize my, let's see, can I make it shorter? Yeah, that's probably a good idea. And then I can go backwards and forwards. So how about picking out some of these exercises? Should we do tangent? Match the trigonometric function with its graph. Oh, okay, so they've got 6 function formulas and 6 function graphs. Which one is which? Well, this is going to be tangent shifted pi over 4 to the right. So which one of these have the shape of tangent? Only this one, right? So it must be this one. And we see, yeah, there's the vertical asymptote, which was, this is pi over 4 to the left. Yeah, so the vertical asymptote, which was at pi over 2, is now at pi over 4. That looks like a negative pi over 4, but that's a hash mark on the y-axis, right? This is negative pi over 4 over here. You can look at the rest of those. Let's get on to 19 through 34. How about number 25 here? The tangent of pi over 4x. Let's go over to our workbench here to see that. Okay. So this is now 5.4, I believe. We're finally on to 5.4. I can't believe it's a snail's crawl here. Well, it's pretty dense material, so I'm not inclined to rush it. 5.4. So we want to graph f of x equals the tangent of pi over 4 times x. So is that an expansion or a compression. It's horizontal, right? Because it's multiplying the input. Is it expanding it or compressing it? Well, pi over 4 is less than 1, right? Pi is approximately 3.14, so that's going to be less than 1. So that means x is going to have to be bigger. So it's going to stretch horizontally a little bit. But more importantly, we can talk about the period. The period of tan is pi, right? It's got half the period, whoops. It's got half the period of sine and cosine. And why is that? Well, you know, the values in the fourth quadrant are the same as the values in the first quadrant, right? Because it's the ratio of y to x on the unit circle. And so if y and x are both positive, you get the same ratio of y and x are their opposites in the third quadrant. Similarly, the fourth quadrant is the same ratio as in the second quadrant. All right, so here's the period of tan, and we want the input to tan to go between 0 and pi over 2, right? Well, but yeah, I mean, in fact, these are not domain values because the tangent is not defined at pi over 2, but we can still use less than or equal and less than or equal, right? Okay, so if we multiply by 4 over pi, which is positive, 0 times anything is 0. That's the reciprocal of pi over 4. And what's 4 over pi times pi over 2? Well, that's 2, right? So we see that this function is going to, whereas the period of tan is oh, I'm sorry, I meant to put pi here. Right? We want the input to go between 0 and pi to complete one waveform. Or maybe we should say between negative pi over 2 and pi over 2. I guess that's why I wrote a pi over 2. That's sort of, the interval from 0 to pi includes a vertical asymptote. If you want to not include that, then you might say, I want the input to go between negative pi over 2 and pi over 2, and then you don't include any vertical asymptotes on the interior of the interval. But here we're just saying, look, this is one complete interval for an oscillation, if you want to call it that, of tangent, right? So this is now going to be 4, right? The reason I paused was because I said, well, we were supposed to stretch, and now 2 is less than pi, but 4 is more than pi, right? So we went from an interval of a wavelength of approximately 3.14 to a wavelength of 4, which is bigger, right? And so where are the vertical asymptotes? I think they're at 2 and negative 2, right? So if we make a table of values for x and f of x here, I think we'd want to say, yeah, negative 2, well, let's say it's 0, we've got 0, right? Tangent of 0 is 0. And then to get to pi over 6, we'd want to have 2/3. Why? Well, what's 2/3 times 1/4? That's 1/6, right? So if x is 2/3, then pi over 4 times x is pi over 6, and that'll get us our old values for tangent. So the tangent of pi over 6 is sine of pi over 6 divided by cosine of pi over 6, right? And do we know what those values are? We'll dial them up on the unit circle. This is 1/2. This is square root of 3 over 2. Yeah. And so this is going to be 1 over the square root of 3, which we also write as square root of 3 over 3, or approximately 0.57. Okay. So what if we wanted pi over 4? Well, we just go to 1, right? And so if x is 1, then tan of pi over 4 times x is tan of pi over 4, which is 1, right? At pi over 4, sine equals cosine, right? They're both square root of 2 over 2, and so you get 1 as the output. And I think we want to go to 4/3 as our next input here. Yeah, if the input to this function is 4/3, then we've got tan of pi over 3, which is square root of 3, and that's approximately 1.732. Now, tangent is odd. So if I change the sign of the input, I also change the sign of the output. So I can just put plus or minuses everywhere, whereas the plus refers to the plus and the minus refers to the minus. And so are we ready to make a plot for this thing? Sure, let's go ahead and do it. Here's the horizontal axis and the vertical axis. And let's say that this is 2 and -2. I didn't say that at plus or minus 2, we're going to infinity. But those are going to be our vertical asymptotes, right? We're going to have another one out here at 4. Should we draw that one as well? And -4, I guess, for that matter. Got a couple of. Are those perfectly evenly spaced? They used a ruler. I think they would be. Okay, so here's what 1 and 2, perfectly evenly spaced. -1 and 2, don't forget to label your axes when you're making a graph. And we're going to plot the points on the curve. So this is actually not a vertical asymptote over here. I had a feeling I was wrong. This is, it's only half of the wavelength is 4, right? So from 2 to 4 is only 2, right? So we wouldn't have completed a waveform yet. Okay. So at 1, we have 1, right? So that's here. At -1, we have -1. That's here. And here's our tangent waveform, curving downwards and then curving upwards. Okay, and then over here, it's going to do the same thing, right? And then over here. Am I running out of lead here? Okay. Yeah, forgive the sloppiness, but yeah, you get the idea, right? That's, I didn't plot, say, so this is 1, here's 2/3 and 4/3. So about 1.7 there and about 0.57 there. Okay, right about there. Yeah. Sure, that looks good. All right. So that was number 25. Did I say that we were doing number 25? This is, yeah, that was number 25. Back to the exercises. How are we doing? It's now the 13th hour. And we're crawling along, but that's okay. No reason to rush things. And so there are a bunch more like that. We'll do some with the shift and the compression. There's both a shift and a compression and vertical and horizontal compression. How about number 50? Here we've got, yeah, there's a lot going on with 50. And I confessed to my biased towards secant and tangent. I prefer those to cosecant and cotangent. Why? I don't know. You get all you need from secant and tangent, and then you don't really need cosecant and cotangent. However, when they come up, you need to be prepared to deal with them. Okay. So I don't want to lose my focus. So I'm going to kind of shift this thing here, and I'm going to transfer this problem over to the workbench here, which I can do by just minimizing that, right? Okay. So this is 5.4, number 50, I think. Was it 50? Yeah. So we've got f of x is multiplying the output is the number 3. So 3 times the secant of multiplying the input is 1/4. And then we also subtract pi over 6 as part of the input. But we would like to, say we've got a vertical stretch by a factor of 3. So that would mean that the intercepts, the y-intercept that was at 1, right? The reciprocal cosine of 0 is 1, is now at 3. Now that 1/4 means we're going to stretch horizontally by a factor of 4. But what's the shift? To see the shift more clearly, we want to factor out that 1/4 from the pi over 6. Do you see that? So I'm going to rewrite this as 3 secant of 1/4 x minus, and what is it? It's 4 pi over 6, which is 2 pi over 3. Oh, that's not quite on the sheet, is it? Okay. Let's see, can I take this away without losing focus? Oh, no. Come back, Mr. Focus. Put my hand there. Okay, so the other trick was to bring this up close. I would focus on that. There you go. That's better. And slowly bring it back down to this, as if we have time for this sort of nonsense, right? Okay, and then here's our problem. Okay, so shall we make a few comments about this? So we have a vertical stretch by 3. We have a horizontal stretch by 4, and we have a horizontal shift by 2 pi over 3. Okay, so if we're making a table of values, which we should do, we might want to start, just put in the middle, I guess, maybe this 2 pi over 3. Just put that smack dab in the middle of our table. And work backwards and forwards from there, right? Because why? Well, because 2 pi over 3 minus 2 pi over 3 is 0. And the secant of 0 is 1, right? The reciprocal of cosine. And 3 times 1 is 3. Okay. So then, can we say something about the domain? Well, the domain, typically we think of, well, let's say if the input goes between 0 and 2 pi, right? That's going to be one waveform. So we want the input to go between 0 and 2 pi. Let's see what that means for x. Is that visible there? Okay. So we can multiply through by 4 and get x minus 2 pi over 3, then goes between 0 and 8 pi. 0 times anything is just 0, right? So multiplying the left side by 4 doesn't change it. Then I want to add 2 pi over 3 to all three numbers, right? Okay. And this is 24 pi over 3. I don't know, how do you want to say 26 pi over 3? I guess we could say that. I mean, it's true, right? So that would complete one waveform. So what's halfway between those? Well, to get the halfway point, we add them up and divide by 2, right? So 2 pi plus 26 pi is 28 pi over 3. Half of that is 14 pi over 3. That. Well, let's see what that leads to. I'm going to put a 14 pi over 3 in my input column. I'm not going to put it next. I'm going to put it out here, 14 pi over 3. Remember, we got a big stretch horizontally, right? So it's not surprising that this is a large value at only halfway through the form, right? And what do you expect to happen here? I expect this to be a vertical asymptote. Let's see if I'm right. So 14 pi over 3 minus 2 pi over 3 is 12 pi over 3, which is 4 pi, and 1/4 of 4 pi is pi. Secant pi is the reciprocal of cosine pi. Cosine pi is -1. Okay, so this is -3. Okay, so I was wrong. It was a wild guess. I seem to be running out of ink. It's not ink, it's whatever they put, graphite. How are we doing? Okay, we're running short on time. I'll just switch over to my 0.7 then, which is not bad. Okay. So halfway between these is going to be a vertical asymptote, right? So let's add these up. So we get 16 pi over 3. Half of that is 8 pi over 3. And, right, that's halfway between 2 pi over 3 and 14 pi over 3. I just think of adding 6 pi over 3, I guess, right, or 2 pi. Okay. Right, the wavelength is 8 pi, huh? Yeah. Sorry. So if I plug that in, 8 pi over 3 minus 2 pi over 3 is 6 pi over 3, which is 2 pi. 1/4 of that is pi over 2. The secant of pi over 2 is the reciprocal of the cosine of pi over 2. The cosine of pi over 2 is 0. So this is the reciprocal of 0, which is infinity, right? Or you can say vertical asymptote, right? So that's where the vertical asymptote is, right? So I can kind of extrapolate the big picture from here. So if I go back 6 pi over 3, that's going to be -4 pi over 3. And I'll get another vertical asymptote. If I go back another 6 pi over 3, I'll be at -10 pi over 3. And then I'll be at -3. And so on, right? But let's just use what we got since we're short on time. In fact, we're out of time. So let's take the remaining negative time. And we started a minute late, right? What happened to my straight edge? Oh no, we've lost focus. We've lost straight edge. Oh, come on, really? This is really gimpy, this cam. I left my other cam at home, my other home. All right, can you handle that? Thank you. So I'll use this straight edge. And see if we can find our way here on the coordinate system, right? So we've shifted to the right, so let's accommodate that by plotting here. So what do I want to do? I want to count by, I don't know, 2 pi over 3. So let's say here's 2 pi over 3. There's -2 pi over 3. Oh, that's not evenly spaced, is it? Sorry. Yeah, and here's negative 4 pi over 3. That's a vertical asymptote, right? So I'm going to draw in a vertical asymptote here and label my y-axis and my x-axis. I'm going to label this 2 pi over 3. So here's 4 pi over 3, 6 pi over 3, 8 pi over 3, right? That's another vertical asymptote. And so at 2 pi over 3, I've got 1, 2, 3 as the output, right? And I don't know what the input was, but so 4 pi over 3, 6 pi over, this is 8 pi over 3, 4 pi over 3, 6 pi over, well, 6 pi over 3 is 2 pi, huh? Okay. But remember, this is a horizontal stretch by 4, so this is kind of a wide curve. So I'm just going to kind of fake the secant curve. And this is only half of the secant curve because the other half is opening downwards, right? So maybe tomorrow we'll get the other half. And that's all we'll have time for. Okay. Any questions about anything before we wrap it up today?
Thank you, Professor.
Thank you. Nice to hear from you. Anybody else? Okay. So let me know if you have any questions. If something occurs to you, send me an email. All right. I'm available that way. Okay, everybody. Bye for now.